Next up is Celia Eddy, data scientist at the New York Times, where they publish over 250 pieces of journalism every day and have a collection of over 20,000 recipes. Celia will introduce us to machine learning-powered recipe recommendations that help their users find and cook the recipes that are most interesting to them. Over to you, Celia.
Hello, my name is Celia Eddy, and I'm a data scientist at the New York Times. I want to tell you today about our Algorithmic Recommendations team at the Times and how we are experimenting with content recommendations, and specifically how we experiment with recipe recommendations. I've been working at the Times in the data science group for almost 2 years, but I actually come from a background in seismology and geophysics research. I came to a career in data science via the Insight Data Science program. So as I mentioned, I am part of the Algorithmic Recommendations team. We're a cross-functional team of data scientists, data analysts, and software engineers. Our goal is to help users discover engaging, relevant, and useful content across New York Times products with a machine learning platform that provides real-time content recommendations. During this talk today, I want to give you a good idea of what exactly our team does to meet this goal and how we do it. So why do we actually recommend content using algorithms at the Times? The New York Times is well known for its editorial judgment, and readers often come to the Times because they want to see the news of the day that is universally important. That is, they want to see the news that editors have decided everyone who comes to the New York Times on that day should see. And this is, of course, a really essential part of the Times' purpose and mission. But that mission is not incompatible with also personalizing content. We need to use the limited space that we have to show content very efficiently and effectively. We sometimes publish hundreds of pieces of journalism every day, and we currently have more than 20,000 recipes in our recipe collection. There is not enough space for promotion of all of this content, particularly on mobile. So by personalizing part of the experience, we can actually help articles reach the people who are most interested in reading them. By using our platform to algorithmically recommend content in certain areas, we free up editors' resources to focus on the top stories and breaking news parts of the report, which are very work-intensive. And then my final bullet point here, typically editors will refresh what they're promoting a few times a day. However, there's often content that is relevant on much longer timescales. There can be articles that are relevant and remain popular for days at a time or even weeks at a time. So using our algorithms, we can learn when assets continue to be popular and then continue to promote them so that they get more exposure and also have a longer lifespan. So where do we actually personalize content at the New York Times? We work in a lot of different spaces right now. We work in the apps, we work on the web, and we also work in email newsletters. So here I'm just going to walk through a few different examples of where we currently personalize content. So to start with the core news apps, our main presence in the app is in the For You tab, where we make personalized recommendations of non-news content based on what you've previously engaged with in the past, what articles you've read, as well as what interests you've actively selected and said you're interested in. On the article page on the web, we power recirculation modules, and these modules direct readers to other relevant articles and other popular articles. To do this, we work in collaboration with editors in the newsroom to define lists of appropriate content, and then from those lists of content, we personalize which articles are shown to which user. We also work with email newsletters. We currently algorithmically curate one daily personalized newsletter known as the For You email, which shows content that is based on interests that you've actively selected. And finally, we also make recipe recommendations for New York Times cooking. We recommend recipes based on sort of recipe similarity with the user's saved recipes, based on the similarity of a recipe to the current recipe page that someone is on. We also make recommendations based on recipe popularity. And so for the rest of this talk, I'll really be focusing on how we make these cooking recommendations. So now I'm just going to give a brief overview of New York Times Cooking for those of you who may not be familiar with it. New York Times Cooking is a standalone product that people can subscribe to either as a single product or as part of a bundle along with our core news product and games products. Subscribers get access to more than 20,000 recipes that have been tested and curated by the cooking editors at the New York Times. And these recipes are made available both on the web and through our standalone New York Times Cooking app. So users who subscribe have the ability to save recipes to a digital recipe box. They can create a grocery list based on recipes that they plan to cook. This is to help with meal planning and to make grocery shopping easier. They're also able to add recipe notes, either just for themselves or notes that other users can see as well. And this is all in addition to sort of typical functionality that recipe sites have that allow users to do things like rate recipes, print recipes, or share them with family and friends. So where are we currently recommending recipes? There are a couple of different places right now. We power a recirculation module on the recipe page that shows recipes that are similar to the recipe that the user is currently looking at. For example, I'm showing here the recipe for the world's best chocolate cake, and we're recommending the similar recipes, chocolate pudding with raspberry cream, and also a yellow sheet cake with chocolate frosting. And so these recipes are recommended based on the assumption that if a user is interested in the current recipe, they'll also be interested in these other similar and very delicious recipes. We also power a block on the cooking home screen on both the web and in apps that shows recipes that we think a user will love based on the similarity of those recipes to recipes that they've previously saved to their digital recipe box. Now, if a user is new, or if they haven't actually saved any recipes yet, instead they get a prompt in this box that tells them they should start saving recipes in order to start getting personalized recommendations in this spot. Finally, we also power a recipe recommendation email that is sent approximately bi-weekly. This email shows recipes that we think users will like, again, based on things that they've engaged with and saved in the past. So what types of algorithms do we currently use to make these recipe recommendations? Broadly, they fall into 3 different categories. We use algorithms that are based on content similarity. So these algorithms measure the similarity of recipes to those that you've read or cooked before. So for one example, for me, I really love this sourdough no-knead bread recipe. So I'm always interested in seeing similar bread recipes or recipes for other things to do with a sourdough starter. We also use collaborative filtering algorithms, where we recommend recipes that have been saved by people who have similar reading history to you. So if I personally really enjoy cooking this skillet chicken with orzo, dill, and feta, I'm really interested in knowing what other recipes are liked by the users who have cooked this particular recipe, since we may have very similar taste in food. And finally, we also use popularity algorithms in order to ensure that we're recommending content that is currently popular on the site. So we use several different NLP algorithms to recommend recipes based on content similarity. The type of recipe data that we use as input for these models includes some combination of the recipe title and recipe author, some short description of the recipe, the list of ingredients for that recipe, as well as any preparation instructions. Some of the algorithms we use for content similarity include topic modeling with LDA, which models each recipe as a small mixture of topics and models each topic as having some distribution of words. We also use doc2vec, a model which calculates document embeddings for each recipe. Both of these models result in a vector representation of each recipe. In order to then decide what to recommend, we take the similarity between the vectors for the candidate recipes and the recipes that the users have previously saved, and then rank based on that similarity. So recipes that are ranked most highly will be the ones that are most similar to the recipes that a user has saved in the past. And to get just a quick sense of how the LDA topic model works, we can look at a couple of examples of the top words associated with the first and second topics for 2 different recipes. So for brownies, these topics include words like flour, butter, baking, egg, pan, dough, and bowl for the first LDA topic. And then for the second topic, it includes words like cake, chocolate, sugar, vanilla, whisk, mixture, egg. So these are all words that are clearly associated with baked goods and associated with baking topics. Then on the bottom, we have an example for a shakshuka with feta recipe. Now for the first topic, some of the top words include oil, garlic, chopped, seed, tomato, onion, and ground. For the second topic, it has words like pepper, bread, cheese, slice, egg. So these words in these first 2 topics tend to be ingredients that are actually in the shakshuka recipe. So for the case of collaborative filtering, we use the alternating least squares matrix factorization algorithm. This algorithm allows us to recommend recipes that have been saved by people who have very similar reading histories to you. So this works by constructing and then decomposing the user item matrix. So for one example, take 4 different users and their interactions with 4 different recipes on our site. So if we consider user 2, they've saved recipe 1, which is a rainbow sprinkle cake. This recipe has also been saved by users 1 and 3. Now, if we're interested in making a recommendation to user 2, we might choose to recommend something that users 1 and 3 also like. For example, this black and white cookie recipe, that's the second recipe shown here. This is because we want to show sort of similar, or recipes that similar people have also liked, under the assumption that these people may have similar tastes in food. If we take user 4, in contrast, they've really only saved recipe 4, a salmon salad. We see that this has also been saved by user 3, and because user 3 has also saved the first recipe, the rainbow cake, we may choose to recommend this rainbow sprinkle cake to user 4 as well. So finally, we also use a variety of popularity algorithms to ensure that we are recommending recipes that are currently popular. Now, we sometimes measure popularity and then make recommendations just based on the raw number of clicks that some recipe gets. But we also have algorithms that are based on conversions. And by conversion, I mean, given that someone has actually seen a recipe, how likely are they to then click on that recipe? This allows us to control for the fact that certain recipes are promoted more prominently than others. Say an editor may choose to put one recipe on the homepage, and that recipe would obviously have the opportunity to get more raw number of clicks than a recipe that was never shown on the homepage. So by measuring conversion, we're able to control for that sort of promotion effect. And then finally, we use contextual bandits very frequently for recommendations within our core news product, and we're just beginning to test them for cooking recommendations as well. Contextual bandits work by exploring the popularity of new content while also continuing to exploit the content that we already know is popular. Some examples for context for bandits can include both sort of user context or recipe context. An example of user context for a bandit might be the geographic location of a user or knowledge about what recipes certain users like to cook. Examples of context, like recipe context, might be the author of a recipe or the cuisine type for a recipe. So now that I've spent some time going over the algorithms that we use, I also want to spend some time talking about our system and how it actually works. So our system is basically composed of 2 main parts. We have a batch training system that is written in Python and a real-time ranking service that is written in Go. All of the system is hosted in Google Cloud and deployed using Kubernetes. So if you focus on the upper right corner of this diagram for now, it shows the algorithm training part of our system, and that's indicated by the green box in the top right. Now we read data from BigQuery, and that includes information about our assets that comes from our internal content management system. And we also read information about user interactions that comes from an internal New York Times event tracker service. Now the algorithm training is all written in Python, and our jobs are scheduled using Google Cloud Composer and Airflow. After model training is done, we then output model scores into a GCS bucket, as well as a Redis memory store so that they can be accessed with low latency by our ranking service. Then for the real-time ranking part of our system, if we want to recommend content in a block on our website or somewhere on our apps, a call is made to our API. This then calls our ranking service, which is able to read data from memory store. Remember, the memory store contains data about model scores for our New York Times assets. Now, we also have a user history service that stores information about what users have read in the past. And that data that goes into the user history also comes from our internal New York Times event tracker service. We also store in user history information about active signals, like any interests a user has chosen to follow or any newsletters a user has opted into. This user history data is stored in Bigtable so that it can be accessed by the ranking service with low latency. So now I want to share a few more details about the model training part of our system. As I mentioned on the last slide, we read recipe content data and user interaction data from BigQuery. Our models are then trained with frequencies that range from once every 15 minutes to once a day, and that frequency depends on the algorithm. For each model, we then output some metadata for each asset, and what that metadata looks like depends on the algorithm. So for a popularity algorithm, for example, We may choose to output click-through rate over the past few hours for each asset. In contrast, for our LDA topic models, the output would actually be a topic vector for each article. These metadata are then saved to Redis, our memory store, where they're accessible in real time. We also save backups of our asset metadata to GCS buckets, and we also save that data into BigQuery in order to monitor our algorithms. So our real-time ranking service fetches the asset metadata from Redis and fetches any user behavior data from our user history service. We can then aggregate this user behavior into some kind of average user history vector that gives us an average sense of what a user tends to read. So one example of this, if we take sort of LDA, we can average all of the LDA vectors of all of the recipes a user has saved in order to get an average sense of the topics that they like in the recipes that they've saved. And the different rankers that we've written know how to understand metadata from different types of models. So, for example, a most popular algorithm would simply rank by click-through rate, which is a scalar value for each asset. For our LDA model, in contrast, we would rank by the cosine similarity between any candidate recipe's topic vector and the average user history vector. So the recipes that are rated most highly here are going to be the ones that have the highest similarity with the average of what a user likes to read and cook. So how do we actually use our platform to experiment? Our API endpoints correspond to experiment configurations. What I mean by this is that for every single place we recommend content on the website or in the apps or in the emails, we have a separate endpoint that points to a different experiment config. Our standard practice is to test multiple variants on each surface that we recommend content, and we typically measure the performance of our algorithms relative to some simple baseline algorithm. And what this control algorithm is really depends on the place that we're recommending content. We're able to really easily test different types of algorithms and different variants of certain algorithms, but we're also able to test different pools of candidate articles and recipes and sort of choose between different candidate pools. In order to track the results of these experiments and recommendations, our API response includes metadata about the recommendations, such as the algorithm that we use to make that recommendation. This metadata is forwarded to our internal event tracking system when an article or recipe is seen or a user clicks on a recipe. We use this metadata both for training algorithms, but also for analyzing the performance of our algorithms and experiments. We monitor the performance of our algorithms on an ongoing basis, and we are continuously refining the experiments that we run in different places on the site and in the apps in order to improve user engagement and just improve overall the user experience. So we've had a lot of success recently recommending content for New York Times Cooking, and we've seen significant lifts in recipe engagement since we started experimenting. Please come check it out at cooking.newyorktimes.com and come and cook some of our amazing recipes for yourselves. Thank you.
Great. Well, thank you so much. And we have a few questions from the audience for you. Let's start with, do you use deep learning for content similarity or older approaches such as PCA or ALS?
Sure. So for content similarity algorithms, we use both doc2vec and LDA algorithms. I think doc2vec can be considered a deep learning algorithm because we're learning a vector representation of our recipes. But I think that's really the one deep learning algorithm that we use here. Otherwise, we use LDA for our content similarity algos. We do also use ALS for our collaborative filtering recommendation algorithms too.
Great. Thanks so much for that. And the second question is, do you take into account when the similar users liked specific recipes? And do you maybe give more importance to recipes liked more recently?
Sure, that's a great question. So the way we take into account sort of similar users liking specific recipes is through our collaborative filtering algorithms. That's an algo that shows recipes that have been liked by people who have similar reading history to you. So if I like some set of articles and there's another person who likes that set plus some other ones, then we'll recommend those other recipes that those users like to you as well. So that's sort of how we incorporate the recipes other users like. In terms of giving more importance to recipes liked more recently, we don't currently do that in our sort of content or collaborative filtering algorithms. We actually wait all of the saved recipes equally. That's sort of an interesting avenue for exploration. Maybe recipes people have liked more recently are things they're more interested in seeing now as well.
Awesome. And the third question we have from the audience is sentimental analysis of comments written in your articles useful?
Yeah, that's also a great question. So right now we don't actually use any of the comment or note data for our recipes in any of our algorithms. That said, it is a pretty rich data set. There are lots of comments for most of the recipes in New York Times Cooking. So it's sort of a good opportunity for understanding more about what users like about recipes. So I think that that's something we're interested in exploring in the future, but at the moment we don't incorporate any information about the comment or sentiment in comments into our algorithms.
Great. And I think we've got time for just one more, maybe two. Do you incorporate editorial judgment into your recommendations?
Sure. So there are a couple of different ways that we incorporate information about editorial judgment. One way that we do this in the core news product is through a rules-based algorithm that ranks articles by their editorial importance, where we measure sort of editorial importance based on where things have been promoted. So for example, we'll give something sort of a higher score if it's promoted prominently on the homepage. And then we can use this sort of editorial importance algorithm in combination with sort of a personalized algorithm to recommend on other places on the site if we do want to incorporate this sort of measure of editorial judgment as well. Another way we actually do this is through sort of lists of candidate assets that we're recommending in each surface. So basically in every different place that we are recommending, we have a different set of candidate articles that we can choose from in that place. And so for certain surfaces, we actually use lists of assets that have been manually curated by editors in order to ensure that sort of assets on those locations have sort of an appropriate feel.
Right, I think we got time for one more quick one. How do you make recommendations for new users that don't have any reading history?
Sure. One thing that we do for all of our surfaces that we recommend content is that we have basically a fallback algorithm that we can fall back to if we don't have any information about users' reading history. And these fallbacks are typically something simple like a popularity algorithm. So this allows us to populate content even in cases where we don't actually have much information about a user's reading history. There are also some situations where we do have some information about like interests that a user has followed or email newsletters that people have subscribed to that they choose to select during the onboarding process. And if we have that information, even if we don't have reading history for that person, we can use those interests as active signals for some of our content similarity-based recommendation algorithms.
Wonderful. Thank you so much. Well, this has been an excellent presentation, and your information has been absolutely wonderful. So with that, we're going to go ahead and wrap this one up. Don't forget to hit the Return to Lobby button, and that'll take you to the next session. We've got David Press coming up with DoorDash, and we look forward to that presentation. See you soon.